Hello, our presentation today will be on the paper multi-resolution diffusion models for time series forecasting, known as Mr. Diff, with Sean et al., with Karthik, Max, myself, and Nawful under Group 2.
So our problem statement, long horizon timescale forecasting is used for forecasting energy, finance, and climate data days or even weeks ahead, and that's quite difficult. Most models will produce single point predictions, which results in no uncertainty estimates. Diffusion models work well with image generation, but early time series versions ignored multi-scale structures. And trends and seasonality operate at different timescales, so a good model should reflect that variance in timescales. This paper's answers to all of these difficulties are to decompose the forecast into resolution stages and then run a separate diffusion model per stage. So some related work prior to this paper. Transformer forecasters like Informer, AutoFormer, FedFormer, and Patch TST improved accuracy, but also produced point estimates. D-linear showed some simple linear decomposition, and that was quite competitive. Prior diffusion forecasters include TimeGrad, which is autoregressive, slow, with no multi-scale structure. CSD high, which is non-autoregressive masking, with quadratic complexity. SSSD, which replaced the transformer with a state space model to reduce cost. And TimeDiff, which introduced future mix-up and autoregressive initialization. Mr. Diff is the first to fold the decomposition into the diffusion process itself.
So with how Mr. Diff works, like Karthik just said, it decomposes the forecast range into 5 stages via average pooling with these given curls here on the slide. So the components could sum back into the original signal. And so as you'll see throughout the presentation, S will be the denomination for stages. Then two, it would train a separate U-Net denoising network per stage. Each stage is then conditioned on the look back window and the coarser stage above it. And then at inference, it would generate coarse to fine, so the diffusion process itself to sum all stage outputs. There are four key components here in getting this to work in our model. So condition the network via a temporal convolutional encoder plus like an MLP fusion. Denoising network where we had convolutional encoder decoder with skip connections. DPM solver plus plus at 20 steps for faster inference versus say the 100 that's required for DDPM, and a D-linear backbone which provides direct forecasting with the diffusion models having residual.
Okay, so our implementation and datasets, everything was built in PyTorch 2.71 with Python 3.9. The training was run on a local RTX 5090, and for fine tuning, we used the SCU Wave HPC Tesla V100. The training setup was relatively standard, Atom W with standard learning rate, weight decay, batch size, cosine decay. However, for early stopping, we had 20 patient epochs with a minimum of 30. We used per window Revin normalization and reported every metric on the normalized data to stay consistent with the paper. So each of the data sets, you have ETTH1, which uses hourly sampling, 7 variables, and the following amount of observations and look back at the horizon. And then ETTM1, which uses 15-minute sampling instead over the same 7 variables. We ran both univariate with just the oil and temperature column and multivariate versions split on 60-20-20 chronologically exactly as the original paper recommended.
So our baseline, the gap that we had, each stage that trains on ground truth coarser components, but at inference receives its own predictions, so errors will cascade. And our stage summation required clean per stage samples. DDPM produces too much noise for this composition to work. The paper describes DPM solver as optional, but our results suggest that it is structurally necessary for any results to be useful or competitive in any way. So you can see here with our baseline that we have with DPM solver, our paper is uh, our baseline is competitive with the paper. In certain situations, like H1 in multivariate, ours is slightly worse. And in certain situations like H1 univariate, ours is slightly better. Uh, it's, but it's roughly the same. And this is when we use DPM solver, which they describe as optional, but is in fact quite necessary.
And I will add with using DDPM, we were magnitudes off. We couldn't get anything close to this without DPM solver plus plus.
Indeed.
So yeah, so jumping in, so switching to a transformer architecture. So when we ran this model over 14 experiments, we found that the diffusion component was actually doing less than 0.3% of the work for what resulted in the prediction, where the D-linear backbone was doing all the work. And this was very surprising in that to match the model as it was described in the paper, but add components to make it work, it really seemed like the paper didn't really use diffusion in the way that they claimed that they did, as all other papers around this subject matter didn't really do this, and there were no papers based off of this paper to now, such that this paper was just it's a leaf node. And so in our learnings, it was interesting to find that to get the paper to or to get our architecture to be as close to the paper as possible, the diffusion component that we had barely did anything. So with that said, using a transformer to try to improve what we built as the baseline, yep, we use transformers. So a single forward pass. Training was 20 times faster. So instead of taking, say, 34 minutes, it took about 1.6. A lower amount of parameters. So in the millions out of the hundred thousands, I think that we set it to 870 something. But before that, when we first implemented it was like 17 million or something. Less computational overhead due to the nature of the computation. So just transformers in general and how this looks. And then key enablers in the final transformer. So these are the three things that we worked on. So channel independent patching plus decomposed paths, attention residuals on the recent moonshot paper that came out this week on Monday, and overlapping patches and hyperparameter sweeps. So I'll go through this quickly. As you can see, with the orange being the D-linear backbone only and the gray being D-linear plus diffusion, diffusion doesn't do anything. And we validated this many times to make sure that we weren't doing anything wrong. It was just off. So switching to a transformer architecture, you can see the 34 to 4.7. There's a 1.6 in there, but this is for a specific case. You can just see the training went a lot faster. And then at the end, when we ran our 30 hyperparameter configuration sweep, it took an amount of time, but it wasn't anything in the hours or days. So this is our first improvement. This is my improvement. So improvement one, CI plus D comp transform with attention residuals. So we replaced the 843K parameter diffusion pipeline. Then we got to work. So this was after realizing we needed DPM solver plus plus. With a channel independent decomposed patch transformer, trend and residual was split by average pooling, each through a shared transformer encoder with its own output head. It processes one variable at a time, no cross-channel attention residuals. They're learned queries that attend over all prior layer outputs. Zero initialized, so training starts identical to standard transformer training. We used the three-member ensemble for diversity, and it was just faster. Here's just a quick overview. You see at the very bottom, the HP sweep. We figured out the best hyperparameters to get this model to outperform just the D-linear baseline with the diffusion aspect. And just a quick overview going from start to finish for adding the attention module. But I feel like this is too much time to spend here, so we'll move on to Karthik.
All right. Our second improvement, which is mine, was having overlapping patches and the iTransformer model. The CI transformer has no cross-variable mechanism, and the sweep confirmed that the H1 multivariate was stuck in this specific range of MAE. So the first half of this is overlapping patches, that is using a stride that is half of what the patch size is. This creates 83 tokens instead of 42 for attention. So this gives attention a lot more to work with. And it's also fixed a bug where up to 7 trailing timestamps were accidentally discarded. The second path of this is using iTransformer, which is a model from a paper from 2024, I believe, that it embeds each variable's full lookback as one token so that attention can run over a 7-channel token for all of the variables. In the H1 multivariate ensemble, we have one iTransformer plus two of the previous attention res models, and that seemed to work quite well. Ensemble works here particularly because the two architectures attend over different areas and different axes and make uncorrelated errors. So you want one for one situation and one for the other.
Okay, so our third and final improvement would be two-scale decomposition. In the original paper, they used 5 different pooling kernels to break the target into different frequency bands. We simplified that and targeted it for our transformer backbone. So we selected 2 carefully chosen kernels, which gives us 3 clean frequency bands: the coarse trend, the mid band, and the fine residual. Each band is fed into the same shared transformer, each with its own dedicated output head. At the end, we should sum the 3 forecasts back together, which doesn't add any extra complexity in the attention layers. The key thing that made this work would be aligning the coarse kernel to the dominant daily cycle and electricity load data. So for ETT-M1, the 15-minute resolution data set, the coarse kernel was set to 96, which is exactly 24 hours. And for ETT-H1, which is the hourly, it's set to 24. And overall, this doesn't add a high amount of overhead. It's just 2 new output heads, which only add 6K additional parameters.
Okay, so we're getting the results. I'll make this quick. So of improvement 1, we beat 3 out of the 4 benchmark numbers. When I say benchmark, this is from the benchmark that we were able to recreate based off the paper. Here we have the verse paper, but the baseline is really what we're paying attention to. So how well do we start? How well do we end? And we ended up 3 out of 4 up on this first improvement.
With overlapping patches and iTransformer, we also end up at 3 out of 4. The M1 univariate, it increases made slightly. That one kind of regresses because the iTransformer model specifically drags the score up a little bit. But overall, this one is also a 3 out of 4 improvement.
So for two-scale decomposition, the best result was on ETT-M1 multi with 0.4081, and ETT-M1 uni is the single best model result across all experiments with 0.1865. There is a regression on ETT-H1 because the lookback window is too short to effectively separate the target frequency bands, as there's only 336 steps as its hourly data.
And so across all data sets, we have them separated by each data set individually. For H1 multivariate, there is strong gains over the baseline on all cases. For H1 univariate, there is also substantial improvement. And for both the univariate and multivariate for M1, it's competitive or better than the baseline. And we have a little graphic here to demonstrate how this works as well. Pretty self-explanatory.
Okay, so for discussion, first we switched from cumulative decomposition, which is what was in the original paper, to residual decomposition. Cumulative gave us MAE numbers between 6 and 32 because errors from the course's stage cascaded all the way down. Residual decomposition fixed that. Next, the original paper used a learned projection. We replaced that with a random projection for every forward pass. The learned weights actually made the train test mismatch worse, so random fixed the distribution gap. Third, our final baseline only uses the finest stage output. The DDPM samples from the coarser stages were just too noisy, which caused poor performance. And fourth, every single component from the paper described, the multi-stage setup, the conditioning, the learned mix-up, and everything made performance worse when we tested it in isolation under the standard DDPM. The only thing that kept it from completely falling apart was the DPM solver plus plus. The paper says that DPM solver is optional, but it is the main thing holding this paper together. Fifth, the cross-channel attention consistently hurt data at the scale. With only 10K training samples and 7 variables, even after data augmentation, there just were not enough examples to go around for cross-channel learning. And finally, we had to disable automatic mix precision. Float 16 downcast was corrupting the noise schedule and breaking the entire diffusion process.
Awesome. And then in the conclusion here, replicating Mr. Diff required solving various unspecified implementation details. Just to have a high level, the paper was vague and their appendix was limited, and we had to take liberties into what they believed in it. As Knopfel and Karthik mentioned, they said DDPM was fine, but it was not. DPM solver was required. So there was the decomposition type, the mix-up projection, the leaky rose slope, which we had at 0.1, and ETTM1 look back. So yes, we had to use DPM solver. There was no way around that. To replicate, we did implement all those variables that I just discussed. We tested all of our comparisons, and we came to say the baseline that we did. When we added the diffusion aspect with the D-linear backbone, we did discover that diffusion really did nothing. And it was very interesting the way the paper posed this, and also how no one else had built anything off of this paper. Transformers ultimately beat out the results in terms of training time and results in general. A lot smaller of a model. Channel independence multiplies the effective training set by D, which proved valuable as any architectural feature. And then in the end, we combined our best results. And surprisingly, given our baseline that we were going against, 2 of the numbers we got, so 2 of the benchmarks we got out of 4, actually beat the paper's reported numbers. So we had a net upside, not just against our own baseline. Here are our references, and thank you for seeing through our presentation.